let's go. I'm a bit unprepared because of the fact of jumping in for the previous one, but let's see how we can make this. All right. Yeah, thanks for this opportunity for presenting this work. The goal here is, I can advance the slides, is describing or providing a framework to measure complexity in computer networks. My name is Jose Moreno. I have 23 years of experience in the business. I'm not coming from the academia, but from different positions in different companies, designing and maintaining networks, as well as helping customers building that, both from a typical network company such as Cisco, as well as a hyperscaler such as Microsoft. In my career, I have seen many people or many organizations building networks that are too hard to maintain. And the consequence of this is more frequent outages, misconfigurations, and human error is the most frequent of network outages, as well as a longer time to fix those outages. When I was working as a network architect, I used to have my 2 a.m. test for network designs, which was the question to myself, hey, would I feel comfortable if I got called for troubleshooting this at 2 a.m. in the morning? And as you can guess, this is not a very objective measure. What is complex for me might not be complex for others, and vice versa. Is there a way of assessing complexity objectively without having to recur to these subjective questions? This is the goal that we are trying to solve in the next 25 minutes. And in this paper, I focus mostly on the upper part of this pyramid. Network configuration is composed of both infrastructure configuration as policy. Infrastructure configuration tends to be commoditized these days or even abstracted away from customers and users. And policy is the bit that is changing most frequently and hence the ones with highest risk of misconfigurations and hence outages. My current employer might or might not have had a major outage with one of these network protocols recently, and that shows the potential impact of these problems for companies that have a presence in the internet. So minimizing this is an objective which is behind a very tangible business. All right, why are networks complex? Well, the first reason is because requirements might be complex. However, we are not here today to discuss that one because most often than not, you cannot change the requirements. But there are other two reasons why networks might be complex. One is because there might be 2 or more options to design your network and you picked the hard one instead of this more simple one. The second is because maybe the network model that you are using because of the vendor you chose is forcing you into some complexity that is actually not required. So these are the 2 exercises that I go over in the paper I'm presenting here. Let's start, before I go there, there's been a lot of studies in complexity of different systems, natural environments, and stock share evolution. And yet, after investigating the most frequent measurements of complexity used there, which tend to be either the Shannon entropy or the Kolmogorov complexity, I decided not to go for those. Why is that? Because the complexity measure I'm looking for should have 2 properties that these 2 metrics don't have. First, it needs to be explainable. If I deem one design to be more complex than another one, I need to explain a person why is that and how to simplify. Second is the goal for this complexity is to prevent human error. And hence, the complexity has to be considered from a human perspective, since humans are the ones making these mistakes, and not from an algorithmic perspective or probabilistic perspective, as the 2 metrics that are proposed in most research out there. All right, having set the context, we can start with our first exercise, which is going to be comparing different designs under the same computer network model. For this, I picked the public cloud. One public cloud I happen to be very familiar with, which is Microsoft Azure. And yet this exercise would be valid for every public cloud out there because the networking constructs are pretty similar. This is actually a question I see often asked by organizations moving their workloads to the public cloud, which is how do I configure my network segmentation, my network policy in this case? I'm proposing here 3 options that are valid in most public clouds out there. We have a topology at the left where network policy is centralized in a single device, happens to be a firewall. Then there's the topology on the far right where the traffic policy, the traffic segmentation policy is spread out over the network. This would be comparable to access control lists in traditional networks or network security groups in other models. And then there's a way in between where you offload some of the complexity, some of the traffic segmentation to the network, and some you keep centralized in the firewall. I see customers before this question very often, and the reasons to go for one or the other are often subjective. So let's try to remove subjectivity here. The first thing that we need to do in order to evaluate complexity is to model the network as a graph. On the left hand of this slide, you can see the graph representing the model that is required to configure that network, which is quite hard to understand. In this case, we have only 24 endpoints, but real life networks could be much, much larger than that. And understanding that one with a human eye is a challenge. So I propose the utilization of a size normalized graph, which you can see on the right, which is essentially a summary of the left by representing not necessarily node, but node types. For example, if you have subnets as a node type, then you would have a single node on the size normalized graph, and the size would be the relative frequency of that node type, as well as the edges between 2 different nodes, node types or vertex types. By doing that, we can now compare our 2 topologies. You can see the full graphs at the bottom. As I warned earlier, it's hard for the human eye to decide which one is going to be the simplest. But if we look at the size normalized graphs on the top, the first intuition is that topology 3 might be the simplest. So these size normalized graphs help for a more natural understanding of complexity. But we are not looking for intuitions here. We're looking for objective measurements. And that's why these are here in this table, the metrics I proposed to evaluate complexity of a network design. I'm going to go briefly over the first ones because the most important one is the one I have at the last column of this table, the IP excess degree, which I will explain what it is. But let's focus on the first one. An initial approximation might be the number of nodes, even normalized by the number of endpoints, which is already a good indication, but not necessarily a perfect one, because you could have a more sophisticated model with more nodes that is easier to maintain than a less sophisticated model with fewer nodes, and we will have an example of that. The next 2 columns are the edges, which I divide in loose edges or loose relationships between vertices and tight edges or tight relationships between edges. There's a big difference, because if you have a loose relationship, that's always a potential for failure. The next 2 columns are the node types, which I distinguish in infra type and policy type nodes. Why is that important? Because many models use infrastructure concepts to describe policy, which is again a problem, because then you cannot necessarily move policy across different regions or environments. And now we arrive to the last one, which is, in my opinion, a very good indicator of how effective a policy model is. Let me explain what I mean with IP excess degree. In a traditional network, when you define that 2 subnets would speak to each other, what you would do is configuring subnet A, you would assign it an IP range, you would configure subnet B, you would assign a different IP range, and then you would go to your firewall of choice and define a rule that allows both subnets to talk to each other. And typically, you would type again the subnet IP addresses that you assigned earlier, which is obviously a problem for many reasons. First, when you are retyping an IP address, you can make a mistake. Second, the topology is dependent on the IP addresses. So if you are going to move this policy to somewhere else, you are going to have to change everything because the IP addresses will probably be different. And third, this is very fragile when changes are happening to the network. For example, if somebody decides to change IP addresses of the subnets, they might forget to update the policy. So in essence, what I'm proposing here as a measure is to calculate the degree of nodes which are of IP address type. And whenever there's an IP address which has a degree of more than one, in essence, is connected to two different vertices in the graph, meaning that the administrator had to type that IP address at least twice, then that's a problem. Looking into this, it's now fairly easy to describe the three topologies that we looked at. If we look at the first topology, there's a lot of duplication. If we look at the last column, there's this 37 IP excess degree. So meaning that the network administrator here had to type a lot of times different IP addresses for subnets, for firewall policies, for access control lists. We don't know with just this number, but it's a number that shows a significant fragility of this design. Topologies 2 and 3 are much more simpler. Much simpler. As you can see, the excess degree is not eliminated, but it's reduced significantly. If we compare topologies 2 and 3, which have exactly the same IP excess degree, we could move to other the rest of the columns. For example, in topology 3, we see that there are much fewer node types. So that gives us already an intuition that reduction of complexity is coming because of the because of the methods to segment traffic are not as sophisticated as in topology 2. And hence it's going to be easier to maintain. Of course, whether a customer goes for topology 1, 2, or 3 here, it's not going to be purely just because of complexity. Other factors will weigh in that decision, such as cost or the functionality that its technology is providing. And yet complexity is one of the most important requirements, and so far there was not an objective way of measuring that. All right, this was the first example where we compared 3 different ways of achieving the same objective, of fulfilling the same requirements on the same platform using the same abstraction model. In the second part of the paper, I analyzed the opposite case, where you have a fixed design and you can deploy that fixed design with a variety of platforms and hence with a variety of abstraction models. Which abstraction models am I talking about? First of all, public cloud. We already went through it in the previous exercise, so let's use that as a baseline. Second, command line interface. This is the way in which network administrators have been deploying networks for the good part of the last 35 years. And a lot of criticism exists around command line interface, but there are few material measurements of why and where exactly command line interface is suboptimal as compared to other abstractions. Third, I picked Kubernetes because Kubernetes is taking the world by storm, and a lot of technologies are moving to that kind of abstraction. So it's gaining a lot of traction, and there's a lot of tooling and ecosystem out there. Fourth, I picked Cisco Application Centric Infrastructure, which is an abstraction model introduced around probably 8 to 10 years ago, which was one of the first attempts to abstract and hide complexity of a network and clearly separate the policy configuration of a network from its infrastructure configuration. So it's going to be interesting looking at this. Of course, there are many other abstraction models out there. There's Juniper Abstra, which in my eyes falls more or less in the same bucket of ACI, being an abstraction model on premises. You have as well hypervisor-based networks, which are similar to public cloud, but let's stick to this four. Okay, caveat here, since we are comparing different platforms, chances are that these different platforms will support different features, and hence the risk exists that we are not comparing this exactly the same thing. I tried to simplify the initial model so that all the features contemplated there are supported in all 4 models. But still, I wanted to put this caveat here since this result should be taken with a grain of salt. All right, let's have a look at the size normalized graphs here of the 4 abstraction models proposed. As you can see here, there's already, in my opinion, at a first glance, the number 2 and 3, Cisco IOS CLI and Kubernetes, seem to be the simplest ones, while the Azure one seems to be the most complex one from again at a first look. But let's have a look a bit at depth at the numbers. If we look at our IP access degree, the last, the far right column, we see that the Cisco command line interface is the one with the highest IP access degree. What this means is that administrators configuring their networks with command line interface, they need to type a lot of times the same IP address. Again, this is one of the reasons why CLI is so fragile as a network management tool. The second thing that is interesting about CLI is that in order to model policy, it's using a lot of infrastructure type configuration, which is the third column from the right. As you can see, there are 4 types of nodes for infrastructure, while there's only 1 for actual policy. So network administrators find themselves having to misuse infrastructure to define policy. If we keep on moving to the to the other new models that we have introduced in the second exercise, we see that both Kubernetes as well as Cisco Application Centric Infrastructure manage to reduce IP access degree to 0, meaning in these 2 models, administrators do not have to copy paste or type twice any IP address at all, which is a huge win, which is and that evolves into a much reduced fragility of this network. Plus, there's a much more balanced proportion between infrastructure node types and policy node types. Now, the difference or a significant difference between Kubernetes and Cisco ACI is the use that Kubernetes makes of loose edges or loose relationships between nodes, while in Cisco ACI, all of these relationships are tightly coupled. As you can see in Cisco ACI, there is a 0 in the L edges for loose edges, while most edges in Kubernetes are loose. Actually, you could argue whether loose couplings or tight couplings are better or worse. The jury is still out there, but I wanted to highlight that difference because, in my opinion, it's a very significant one. So I wanted to show here that, for example, the command line interface has a lower number of nodes that say our initial topology that we looked at with Azure, with public cloud. But the IP access degree is showing us that it's a much more fragile network to maintain. This is the one I wanted to highlight when I mentioned at the beginning that while the number of nodes could be a good approximation to the complexity of a network, is by far not enough to describe how prone to mistakes that network is going to be. Right, I'm looking at the time, so I think I'm going to start wrapping up and open for questions if there's any. What's the output? What's the corollary of all these discussions, all these metrics? Well, if I have to distill 3, would be for different audiences. If there's anybody listening to this or reading the paper that is in the business of designing networks, such as service integrators or consultants, complexity is going to be a criteria to choose between different designs. And the result of this paper would be that there are objective ways of measuring complexity of each design, and the ask would be not to resort to subjective measures, such as the one I admit to have used in the past about my 2 a.m. test when deciding for one design or the other. The second is if you are in the business of developing networks. if you create a network to sell to organizations, you will as well have to create a network abstraction to manage your network. My ask to you is first, please do not force your users to copy paste IP addresses or any other information or enter any kind of field twice. And second, if you use infrastructure concepts to define network policy, maybe the acceptance by traditional network administrators is going to be better at the beginning, but at the end, the policy defined with such infrastructure concepts is going to be difficult to maintain and confusing in the long run. All right. So with that, those were the concepts I wanted to highlight for the paper. And if there's any question, I would be happy to answer them.